Hi, I'm Piyush, and in today's video we are going to discuss another LeetCode hard problem which will definitely help you improve your dynamic programming skills. Now before you get started, I would recommend that you watch a few prerequisite videos that I've listed down in the description below. They will help you grasp the strategies that we're going to discuss today. And so let's get started. So the problem given here is that we have an array storing the stock prices over several days, where every index of the array denotes the day. Now the task for us is to find out the maximum profit that one can gain by simply buying and selling stocks, with a constraint that you can buy and sell a stock at most k times. Note that you must sell a stock before buying again. Let's take an example. Suppose you have 4 days of stock data and the corresponding prices of the stock on each day. When k is equal to 1, or when you can only buy and sell a stock at most once, the solution is quite simple and intuitive. We can keep track of the maximum stock price from right to left in the array, or basically from the 4th day to the 1st in this case, and we can update the max difference of the prices we have seen so far. So let's begin with the last day's stock price as 20, and we update the current max price and the max difference as 0. Note that this means that there is no use of buying and selling a stock on the same day. Well, now we iterate from right to left and we update the max difference or the max profit accordingly. Now once we reach the second day, we update the current max price seen, since 21 is more than 20, and we move on. Finally, we reach the first day and we update the max profit as 19, and that's the answer. Well, that was quite simple. But when k is greater than 2, such a greedy approach will not really work, since how do you even keep track of the max profit given k possible buying options, right? Let's go back to our whiteboard to understand if we can find any subproblem that can help us out. Intuitively, let's try to find a brute force approach first and find all possible ways of buying and selling. We'll then use this to devise our recursive DP algorithm. Well, so the problem we have is that there are n days worth of stock information and we need to maximize our profit with the constraint of k. Let's say we buy a stock from day 0 or the first day. We can now sell the stock on either the second day or the 4th day or even the last day. Who's going to stop us? Well, now the thing to note over here is that we have n-1 options of selling a stock if we buy it on day 0. So one possible pair of buy and sell days is basically buying the stock on day 0 and selling it on day 3. In this case, if you notice, we can independently find the max profit from day 4 to day n and then add the result to the current profit made. Another possible pair is to sell it on day 1 instead of day 3 and then again independently find the profit from day 2 to day n with a reduced k and then add it to the current profit made. Now the interesting thing to note here is that finding the max profit from day 1 to day n with k as m-1 is another subproblem that will help us in this case. Now since there are n-1 possible selling options for a stock we bought on day 0, we can iterate over each of the selling options and then maximize the total profit. Note that we need the max profit from the other part of the array once we sell a stock, which itself is a different subproblem as we discussed. We need to also consider not buying the stock on day 0 as well, right? In that case, we simply find the max profit from day 1 to day n with k unchanged. So the subproblem we identified is as follows. Find the maximum profit that you can make from the current start day to day n with a given constraint of k. Well, let's now jump into step 1, which will make it more clearer. Now in step 1, we'll define the function and the states, or rather the parameters of the function. Again, as discussed in the video about recursion, we need to define the problem that was given to us in terms of states, and we will also define what this function should do. In this case, the function should return the maximum profit that it can make from the start day and the current value of k. So the state of each recursion node is identified by the start day and k. Now the stock prices array has the price of the stock for each day, which won't get updated on every recursive call. Well, now in the next step, we will take the recursive leap to solve the subproblem and use it for computing the profit. So given a start day and a value of k, we have two options as we discussed. Either we buy a stock or we ignore this day and move on. Now if we buy this stock, we need to find the day on which we will sell this stock as well, right? So let's assume we buy the stock. In that case, we will iterate over from the next day to the last day, and we will choose the selling date which will maximize the profit that we can get. So for each option for the selling date, we will first compute the profit by selling the stock on this day and then find the max profit that we can get from the remaining days with a reduced k. Note that this is the recursive leap we were talking about, where we are calling a subproblem with parameters as start of day plus 1 and k minus 1, assuming that this recursive call will correctly return us the max profit from the rest of the array or the rest of the days. Finally, we update the max profit that we have observed so far if necessary. Well, now we can also choose not to buy a stock, which means we need to find the maximum profit that we can get from the remaining days without decreasing k. Note that we are again making a recursive leap to find the max profit from the next day with k unchanged. Now finally, in the inductive step, we solve for n and we return the maximum profit that we can get from both these cases. We now still have to figure out what to do in the base case. Now to identify the base cases, we need to understand what can happen when k goes to 0 as we are decreasing k, and what can happen when start of day reaches the end of the array. So if k goes to 0, we cannot buy any more stock, right? In which case we must return 0. Similarly, when start of day reaches the end of the array, we also cannot buy any more stock and we just return 0. Well, that's it for the recursive bit. In the dynamic programming video, we discussed that if we can find overlapping subproblems, we can actually cache them later in order to save processing time by not processing them again later. So let's check if there are any overlapping subproblems here. Now let's consider two scenarios. In the first scenario, we buy a stock on day 0 and we sell it on day 1. And again, we buy the stock on day 3 and then sell it on day 5. In the second scenario, we buy the stock on day 0 and we sell it on day 3, and again we buy the stock on day 4 and we sell it on day 5. Now in both the cases, if you observe that we will have to solve or find the maximum profit we can get from day 4 with k minus 1 maximum available buy sell options. This means that there are overlapping subproblems which we can simply cache. Now the recursion state for our subproblems are identified by the pair of start of day and k, and thus we can create a 2D cache of size n cross k, where n is the number of days and k denotes the maximum number of times we can buy a stock. Note that start of day can go from 0 to n, while k can go from 0 to k. Well, with this in mind, let's analyze the time complexity for this problem. So there are n cross k states, and for solving every subproblem, we take another big O of n time for finding the selling date, while the other operations take constant time. So the total complexity becomes big O of n square cross k, while the space complexity is big O of n into k for the memoization table and big O of n for the recursion stack. Now the solution that we have over here is quite intuitive. But can we reduce the time complexity further? Can we do something with the solution to improve the overall complexity? Well, there are two options. We either reduce the number of states, which in this case is just tracking the start of day and tracking k. Well, this doesn't seem to be a possible option. Well, the second option is, can we do something with the computations that are happening in each recursive call? Well, let's go back to step 0 and investigate further. Well, let's now see if we can find any other subproblem. So we have n days and we are given k. Now we can buy a stock on a particular day and sell it on another day, right? That is given in the problem. Now let's assume we buy it on day 0 and then sell it on day 3. And again, we buy it on day 5 and we sell it on day n. The total profit we get is minus 4 plus 10 minus 3 plus 8. Now notice the alternating signs of minus and plus when we buy and sell a stock respectively. If you have now figured this out, I can sense the aha moment you guys might have. If you notice, our goal is to maximize the sum of the values, and to rephrase, if we buy a stock on a given day, we subtract the value of the stock, and if we sell a stock on a given day, we add the value of the stock to the total profit. Now we can reduce the problem to finding the sum with such alternating positive and negative values with a given constraint of k. Now notice that given this number k, we can at max have k negative values and k positive values. Intuitively, we can simply add another state to our recursion. Let's call it is_by mode, which will simply keep track of the current mode of operation. If is_by mode is set to true, we simply buy a stock and we subtract the value from the profit we make and then add it to the profit we make from the rest of the days with buy mode set to false to denote that we have to sell this stock next. Well, now this helps us eliminate the big O of end search we were making to identify the selling date, since now we are simply finding the sum and trying to maximize it, and is_by mode keeps track of the negative and positive signs. Now we can also skip this day and ignore the current day's price, and in this case we can simply return the max profit that we observe from the rest of the days with buy mode set to true, denoting that we haven't bought a stock yet. Now similarly, in case is_by mode is set to false, we can sell a stock and we add the value to the profit and again recurse to find the max profit from the rest of the days with buy mode again set to true. We can again ignore this day's price as well for selling the stock, and in this case we can simply return the max profit we observe from the rest of the days with buy mode set to false. Now this solution might not be that intuitive at a first glance, but this optimization helps us identify the importance of finding or fiddling with subproblems. So the problem reduces to finding the maximum that we can get from a given start day and the constraint k with a new state of is_by mode. Let's now move to step 1. Now this step is similar to what we have seen earlier, where we define the function find max profit, which should give us the maximum profit which we can make from the given start day with the constraint k and with this newly added state of is_by mode. Now in the next step, we will take the recursive leap of faith again to solve the subproblems and later use it for computing the total profit. So given a start day, a value of k and the buy mode, we have a lot of options at play. So if buy mode is set to true, we can either buy a stock on this day or ignore this day's price and move on. Now if we buy this stock, we need to take the recursive leap and compute the maximum profit we can get from the next set of days with is_by mode set to false. Notice that we don't update k yet, since we haven't sold this stock yet, or rather we haven't yet found the selling date. Finally, we subtract this day's stock price from the current profit found and stored the result. We can also choose not to buy the stock, which means we need to find the maximum profit that we can get from the next day without updating is_by mode state. Finally, we update the max profit in the inductive step by taking the maximum of the two options. Similarly, if is_by mode is set to false, we have two options again. We can either sell the stock on this day or ignore this day and move on. Now if we sell the stock on this day, we need to take the recursive leap and compute the max profit that we can get from the rest of the days with is_by mode set to true. And notice that we now have to update k as well, since we have found this buy-sell pair. Finally, we add this day's stock price to the current profit found and store the result. We can also choose not to sell the stock on this day, which means we need to find the maximum profit that we can get from the next day without updating k and the is_by mode state. And lastly, we update the max profit in the inductive step by taking the maximum of these two options and we return the result back. Well, we now still have to figure out the base cases again. Now to identify the base cases, let's take one step at a time. Let's find the base case when buy mode is set to true first. We discussed earlier that we need to understand what can happen when k goes to 0 as we are decreasing k, and what can happen when start of day reaches the end of the array. In both these cases, we have seen that we cannot buy any more stock and we simply must return 0. Now if buy mode is set to false, K can never be 0, right? Since K is only updated when we sell a stock and K is not yet updated when we bought the last stock. Well, the current day can still reach the last day or the end of the stock prices array, right? In which case we simply sell the stock since there are no more stocks available after this. So we simply return the positive value of the stock price on this day, denoting that the stock is sold. Well, that's it for the recursive bit. Now we have seen earlier in the first solution that there can be overlapping subproblems. Now let's recap the two scenarios that we have seen. In the first scenario, we buy a stock on day 0, sell it on day 1, and again we buy a stock on day 3, sell it on day 5. In the second scenario, we buy a stock on day 0, we sell it on day 3, and then we buy it on day 4 and sell it on day 5. Now for both these cases, we will have to solve or find the max profit we can get from day 4 with a reduced K. This means that there are overlapping subproblems which we can cache, right? Now the recursion state in our solution is identified by the start day, the given K, and the is by mode state. The start of day can go from 0 to n, while K can go from 0 to K, and is by mode has only two options. Thus, we can create a 3D memoization table with the given states with the size of the cache as n cross k cross 2, where n is the number of days, k denotes the maximum number of times we can buy a stock, and 2 is for the is by mode state. Now let's analyze the time complexity before we implement the solution. So there are n cross k cross 2 states, and for solving every subproblem, we now take a constant time. So the total complexity becomes big of 2nk, which is equivalent to big of nk, while the space complexity is again big of 2nk for the memoization table and big of n for the recursion stack, which can be written as big of nk plus big of n. Now let's jump towards the implementation. So at first, we define the recursive function as max k profit that takes as input the list of stocks, the current day being tracked, the remaining k, and the is by mode state. We will first draft the recursive function and then optimize it further using memoization. As discussed in the earlier part of the video, depending on the is by mode state, we will either add or subtract the value in the current index. We can also ignore it. So if is by mode is set to true, we need to take the maximum of either buying this stock or not buying this stock on this particular day. So if we buy the stock, we take the recursive leap to find the max profit from the next day with k minus 1 and is by mode set to false. And then we subtract the stock price on this day to denote a stock being bought. Similarly, if we skip this day's price for buying, we simply skip the day and we again take the recursive leap to find the max profit without updating k and is by mode. Now, if is by mode is set to false, we again have two choices of either selling the stock or not selling the stock. So if we sell the stock, we take the recursive leap to find the max profit from the next day with is by mode set to true, and then we add the stock price on this day to denote a stock being sold. Similarly, if we skip this day's stock price for selling, we can simply skip the day and we again take the recursive leap to find the max profit without updating k and is by mode. Finally, we update the base cases as discussed. If is by mode is set to true and k reaches 0 or we reach the end of the prices array, we cannot buy any more stock, and for both these cases we return 0. Now if is by mode is set to false, k can never be 0 since k is only updated when we sell a stock. Well, as discussed previously, current day can still reach last day or the end of the stock prices array, in which case we simply sell the stock since there are no more available days to sell after this. So we simply return the positive value of the stock price on this day, denoting that the stock is sold. Now we will optimize the recursive function. So we will define a map for caching the intermediate results of the recursion. We will use a pair of pairs to store the states of the recursion, that is the current day and the remaining k, and the is by mode state, which will be a boolean. The map will store the max profit for the states. We will now simply cache the results and we update the statements accordingly, and if we have already computed the results earlier, we simply return the result. Cool, so let's submit it and it's passed. And that brings us to the end of this video as well. If you have liked this video, do subscribe to my channel and do share it with your friends. I would recommend that you check out trilab.io's problem archive, where you will get more such problems and complete solutions in C++, Java, and Python. And these are the problems that I have personally solved during my interview preparations and algorithmic preparations as well. So I'm sure they will help you as well. Cool. See you in the next video. Have a good day. Stay curious. Bye.